Hi everyone, I'm Jimmy from Nanjing University. Today I'm going to present our new work, Multiple Importance Reweighting for Path Guiding. As we know, the efficiency of one-color rendering is highly dependent on the quality of the sampling distributions. So the path guiding process provides an iterative fitted distribution from historical samples. In each iteration, we first generate a new sample set from the current distribution. Then, we fit a new distribution from the current sample set. Ideally, the quality of the distribution will become higher and higher. But what's the final estimation or the final rendering? We know that the first few iterations have high variance, so early works only use the last iteration samples to generate the rendering images. Well, let's state the problem more clearly. Each guiding iteration generates a noisy image. How to combine these image samples? Generally, since we focus on this problem, we don't want the samples from early iterations to be completely wasted when we generate the final image. The most famous practice is inverse variance weighting, which means we allocate the weights proportional to the reciprocal variance. But in general, the variance are computed using the same sample set of the image estimates. Thus, people average the variance across the whole image to decorrelate it. Well, this looks a bit too coarse, and we want to make it more fine-grained. In addition, this weighting scheme doesn't use the distribution information. Yes, we have the guiding distributions, so definitely they can provide more information about these samples. That's why we want to use them. More practically, it may introduce fireflies from early iterations to the final rendering. More specifically, we observe the variance changing tendency differs across different regions in both the image space and the path space. In this first example, you can see the tendency of these two different image blocks are a bit different. And in the second example, the contribution of these two different light sources, red and green, they are also very different. This motivates us to consider the sampling quality in path level. Therefore, our key idea is to introduce a path level weighting factor, Wi. And when we write down the formulas mathematically, we can find it identical to multiple importance sampling, or MIS, which is well known for rendering communities. So just like traditional MIS, we also have to do the choice of weights. We found the balanced heuristic introduced by Rich decades ago has provable consistency under some conditions. This was comprehensively discussed as adaptively multiple importance sampling in statistics literatures. Here the word adaptive refers to adaptive importance sampling, which means the sampling distribution is changing according to the samples. This corresponds to the spirit of path guiding. To make full usage of the variance statistics, we also tried variance via MIS weights, but we found the difference is not evident. Here we provide a one-dimensional example. Here we show the target function and the proposals in each iterations. As you can see, our method with balanced heuristic has the lowest bias among different combination methods. And our variance is much smaller than inverse variance weighting. Now we are really curious about how does it works. The behavior of our method is to weight up the well-fitted regions and vice versa. If some regions are good, we will let them contribute more. But what about correlation? Since the weights and the estimations share the same sample set, they are naturally correlated. We know when the random variables are interdependent, we can't just expand the product of expectations to the expectations of products. So when we use reweighting, we are no longer unbiased. But how much does this method benefit from correlation? To find the answer, we provide a proof-of-concept experiment. In this experiment, we divide the samples into two parts. We split half of the samples to the image and the other half to the distribution. And the result looks promising because we found the decorrelated variant succeeded to keep most of the variance reduction. So where does the variance reduction comes from? Well, note that we are essentially using a matrix distribution to weigh samples, and a matrix distribution is usually more conservative. Thus, this process essentially denotes the distributions and the sample weights, although we didn't change anything about the sampling process. In addition, a matrix distribution leads to variance reduction potentials further. Since the mixture is more conservative, we can use finer subdivisions, both spatially and across iterations. And this indeed leads to higher distribution quality and lower rendering variance. Unfortunately, a complete reweighting process needs to access to all the distributions and path samples. And storing all the path samples is expensive and almost impractical. Therefore, we maintain a fixed size buffer with constant storage for path samples. When the limit exceeded, we immediately throw away low-weight ones. To reduce the bias it may cause, when throwing, we reweight the thrown sample, still using the partial mixture. And as a result, this could maintain similar variance and bias in many cases with the complete method. Compared to discarding all training samples and inverse variance weighting, our reweighting can achieve lower variance. And this superiority is almost consistent for shorter renderings. And the bias also decreases as time goes by. Compared to firefly removers, our bias is much lower. Our work demonstrates the first pass-level practice for combining different guiding iterations estimates. But during our explorations, we also find some limitations. The storage and computational cost of our method is relatively high, and we believe this is a somewhat intrinsic limitation. There may be some further variance reduction potential by reweighting during training, which also aligns with the original adaptive multiple impedance sampling. However, we found the bias is higher, but the variance reduction is not evident. Finally, how to adapt our method with advanced sampling techniques and complex distribution representations still deserves future work. Thanks for listening.